All right, so we've covered arrow pushing with mechanisms. The other main way you'll see arrow pushing is through resonance structures. And then we go back to our kind of little matrix analogy, right? Where you see kind of letters and stuff, and then you see something more complicated. So the real th same thing with our molecules. So for example, if we have phenol over here, that's kind of what we look like, right? It looks like a neutral molecule. We see the carbons, we see the hydrogens, we see the lone pairs, but we see beyond that as well. When we actually think about phenol, what we also see are some partial charges. So what we can see is we can identify that these carbons right here, these three carbons, actually have a partial negative charge. And since we know electrons kind of are the action guys, they do stuff, right? These partial negative charges probably indicate that the molecule is going to be most reactive at those spots. And so why do we have these resonance structures and whatnot? It's because real molecules are complicated, right? They're not just simple atoms with just doing simple things, right? The real structure is a weighted average of our resonance structures. And if this is something that's kind of complex to you, check out my playlist, OChem Part 4, especially video 4.6. That'll kind of give you kind of some ideas here if you need more expansion. But of course, feel free to kind of talk to me, stop by office hours, that kind of thing. We really want to master these core skills. So whenever you're trying to figure out what the real quote unquote molecule looks like and you're thinking about partial charges and resonance structures, you're probably asking yourself, where do you want to start? And so this is something that's a bit of an art form, right? It takes practice, it takes skill, but just some general tips are you want to start at charges, whether they're positive or negative. They probably are going to indicate some kind of reactivity or some kind of resonance structure starting there. The other part is lone pairs, right? So if you see atoms with lone pairs, they might be doing something. And then finally, pi bonds between atoms of different electronegativities, right? So say, for example, like a carbon and an oxygen, right? The oxygen is going to want to pull those electrons, and that might start a chain of resonance structures. Um, Resonance structures usually at some point involve pi bonds. And if you're thinking about what a pi bond is, it's the second slash third bond in a compound, right? So for example, if you draw a carbon-carbon double bond, the first one of those bond is going to be a sigma bond, and then the second one is going to be that pi bond, that bonding between those unhybridized p orbitals. Some other things to keep in mind when you're drawing your resonance structures is don't break the octet rule. And in resonance structures, since they're just a weighted average, right, it's still the same molecule. We're just drawing different frames of it. We're not going to break any sigma bonds, right? We're only going to move around lone pairs and pi bonds. So let's take a look at just two quick examples. We'll have phenol on the left side. We'll figure out how we got those charges that we saw earlier. And then we'll have benzaldehyde on the other side. So when you take a look at both of these molecules, we notice neither one of them have charges, so that's not really going to help us. The next thing we can think about is lone pairs. So we know that this oxygen has two lone pairs, and then this oxygen on the right also has two lone pairs. I'm just going to bother to draw one of them. So we can think about pushing this oxygen to the right side, right? What if we took that lone pair and created a bond with it? Well, if you think about that, that's not going to work because then you're going to give hydrogen too many electrons, right? You're going to break the octet rule. Except for hydrogen, remember hydrogen only wants two electrons, so it's really the duet rule for hydrogen. So we can't move it in that direction. Well, what about in the other direction, right? What if we take this lone pair and transform it into a bond? Well, if you think about the issue there, then we have this carbon right there that already has an octet rule, already has a filled octet, so we can't just do that. However, we do have a pi bond, and as I mentioned, we're usually going to involve these pi bonds. So we can turn this lone pair into a pi bond, and then what we can do is we can take this pi bond and then turn it into a lone pair. And then if you think about the bonds formed, the bonds broken, you should end up with this structure right here, right? And now you can notice, oh, wow, look, this carbon right here has this negative charge on it. That's where this partial negative charge came from, right? From this resonance structure. And then after that, we can kind of continue our compound. Now we have a charge. Now we have a place to get started. If you have both a positive and negative charge, generally go with the negative one because it represents electrons. So we can take this lone pair that's represented by this negative charge. We can transform it into a pi bond. However, then we're breaking the octet rule. So we can do what we did last time and just take this pi bond and turn it into a lone pair. And then we can repeat and do the same thing again, right? Take this negative charge that represents a lone pair, turn it into a pi bond, and then take a pi bond and turn it into a lone pair. And then, of course, we could continue on with that. We could take the lone pair, turn it into a pi bond, and then take that pi bond between the carbon and the oxygen, turn to a lone pair, and then we'd end up with our structure right on top. And so our real structure of phenol, the real molecule, it's a combination of all these, a hybrid of all of these compounds, in which case these three carbons have that partial negative charge, right? And that's what we need to be able to see as organic chemists. Take a look at an example on the right, right? Again, we don't see any charges. So next thing we can think about is lone pairs. So maybe we could think about taking this lone pair and then moving it down. Well, if you think about what's going to happen there, is you're going to start breaking the octet rule, right? That carbon down there already has four bonds, one to a carbon, two to the oxygen, and then one finally to the hydrogen that we don't have to show, but it is there in that this aldehyde, right? Um, and so we can't do that because we can't break the octet rule. And what we'll notice is that there's no pi bonds around to move, right? On the left side, whenever we're like, ooh, if we do this, we're going to break the octet rule, we could then say, oh, but then we could move this pi bond down. Whereas if we try to do this in this compound, we have no pi bond to move around. However, we do have a pi bond between atoms of differing electronegativities, right, between oxygen and carbon. And if we think about it, oxygen is more electronegative, so logically it makes sense for the electrons to go from the bond onto the oxygen because it's the more electronegative atom. So go ahead, pause the video, think about what your structure is going to look like. And then there it is right there, right? And so now what we see is we have a positive charge and a negative charge. Yes, we could move that negative charge to recreate that pi bond, but then we're just right where we started here. So here we have a positive charge. If we think about what that means, remember our positive charge doesn't mean that the positive charge is going to move. Electrons do the movement. So when we have a positive charge, the electrons move here. Right? Don't try to move around positive charges. Don't start your arrows at positive charges, that kind of thing. So we have this pi bond right here. We could think about just turning this pi bond into another pi bond, right? So that's that bond to bond change. So again, pause the video, think about what your resultant structure is going to be. And you should end up with this structure right here. And now we can just repeat this process, right? We've got this pi bond next to a positive charge. We can just turn the bond into another bond. And then one more time. Remember, we're moving the electrons, not the positive charge. The positive charge is just moving around as a result of the electrons moving. And then if we think about mentally superimposing or hybridizing or combining all of these resonance structures, what we end up with is our structure right here that has these three carbons as having now a partial positive charge. And so again, the whole idea here is we have these simple skeletal structures, but they reveal complex molecules, and we can help understand them through these resonance structures. And of course, the key here is to practice.